First, I wanted to thank Susanna and Luis for organizing this very wonderful meeting, and also for many years of friendship and collaboration. And I'll have more to say about that later. I'm going to give a very specialized talk that deals with the properties of the gas in the inner regions of protoplanetary disks. And it's through the lens of my own personal research and attempts to understand that gas. I apologize in advance that I don't include a lot of references to other work. And I would like, of course, for you to interrupt me if there are any questions as we go along. Now, although I'm going to be talking about gas, one must admit, of course, that we have several decades of study of disks, of these kinds of disks, through imaging of the dust. And I have here this famous case of a very active and embedded source right down here, and the disk is there. And the main point for my showing this, in addition to saying that I will also come back and emphasize the importance of the dust, that the scale of these protoplanetary disks are hundreds of AU, and that my interest in the physical properties and the dynamics of accretion and jet production and so forth take us down to the few AU. And so we're talking about, in terms of imaging, having to go to tens or several milliarc seconds. Now, we can learn a great deal about these disks by studying the dust in more detail, and in particular, the spectral energy distributions. And here's a very crude one, but it deals with a special kind of disk I wanted to mention, just to emphasize why these disks are so interesting. And there's a class of these disks which have reasonably large holes. So there are several hundred AU in size, but they can have 10 to 40 or more inner holes. And those are called transition disks. And this is a particularly interesting one, like calcium 15, where there's very likely a extrasolar planet associated with the disk. Now, here we have a spectrum, and there's a stellar part starting, in the few micron range. And then outside, you generally see the irradiated dust in the outer regions of the disk. But in this kind of situation, in transition disks, there's an important region that's missing in the 10 micron range. Here's the famous silicate feature. And in order to model these, there are various things that are done, and this is just an example by Williams et al., who also made this very beautiful image at whatever is about 800 microns of this particular transition disk, and you can see the hole in the disk. Now, one can, of course, ask about imaging in the gas, and that, of course, has been done to some extent, but is in a very active area now with new data from ALMA. So the reason for discussing the gas, of course, is that it is often the major mass component of the disk, and there are all kinds of things that we can learn about planet and star formation by studying the gas. So the goal is to understand the physical properties of the gas in the inner regions, its chemistry, whether it's oxygen-rich or carbon-rich. Are there interesting molecules like water? And then, of course, the gas plays a very important role in the dynamics of the bodies that form the planets and then in the motion of the planets itself after it has formed. Now, we're fortunately, after, I guess, almost 2 decades of being interested in this subject, to be at a time when we can make many different kinds of gas measurements. And these range at least across the electromagnetic spectrum from the near-infrared to the millimeter. And the near-infrared is especially important because it's ground-based, and with large telescopes and special instrumentation, we can get very high spatial and spectral resolution. And historically, the near-infrared has been an important way of detecting CO very close to the young star, as well as some other molecules. We're in the era of space or airborne spectroscopy, and here we're talking about going from the mid-infrared to the far-infrared with these various missions. And I'll be discussing some of that data or referring to some of that data in a few moments. And then, of course, there's this wonderful area of radioastronomy where we are getting many beautiful results from the existing arrays, and then, of course, now from ALMA. Now, with this buildup of the observational prospects, I have to say, well, we also need to have good models to help in the interpretation and understanding of what's observed. And that takes me to the subject of the talk, which is thermochemical modeling of disk atmospheres. And I'll try to explain that now in a little bit more detail. First of all, maybe it's worth also discussing the beautiful data that's been obtained across the electromagnetic spectrum. Spitzer was perhaps has been surprisingly fruitful, and essentially this is a spectrum from Spitzer for a T Tauri star, and essentially you get similar spectra for any one of these that's, luminous enough to be detected. And there are lots and lots of lines here, and most of them come from the OH radical or from water. There's some organics that are present, quite a few, and then there's this neon 2 line, which I have been particularly interested in because it's the signature of X-ray radiation from the star onto the disk. Here is surely incomplete tabulation I've made, and it's incomplete because I've made it, of the molecules that have been detected across the wavelength bands, and the ones for which one can get very extensive data that is easy to get in many T Tauri stars are in boldface, and especially CO and water and OH, and also these others. And you can see that we use here a variety of bands, the ground for the rotational levels of H2, the far infrared for HD, for which there's only one detection, and then both near infrared, but especially the mid infrared for all these other guys from Spitzer. And then Herschel has contributed also in the detection of water and CO, and of course the fine structural lines of these atoms. So there is and will be even more ample detailed spectroscopic measurements of the gas in these disks. Now, the conceptual picture that I have, and of course is based on other people's work, is this cartoon of the very inner region. So there's no core, or infall, but only the inner regions where we have a flared disk, and these disks are, as I mentioned, strongly irradiated by the stellar radiation, and they do get some ionizing radiation, but the ionization level is very low, except in a kind of a hot corona that's above this main disk. So what we have here is basically we have this disk, and we have from the star, we have a variety of radiations. In addition to the basic optical infrared, we have far UV radiation, EUV, and X-rays. And and a lot of what I'm going to talk about is associated with this is irradiation. And the reason for that is that it's somewhat like a stellar photosphere. What we see are the lines that are strong enough to rise above the continuum, and those are the lines that are formed in the atmosphere of the disk. Now, I want to mention here, of course, what I'm doing is extending in some small degree the path that was set by Nuria and Paola in their early and continuing work on the study of irradiating disks by stellar radiation and other radiation. Now, one other comment that I should make here is that that in addition to the fact that all these radiations are different in the sense that they interact with matter in different ways, the densities that we're talking about here are very high compared to, say, dense cores and the general interstellar medium. So we're talking about densities that, say, if this is 1 AU, at the top of the atmosphere are 10 to the 7th hydrogen nuclei per cubic centimeter, and go up several decades to, 10 to the 10, 10 to the 11, so forth. And so in many cases, although our experience from molecular clouds is very useful, one has to be very careful that when you apply concepts having to do with heating and cooling and abundances, you have to be careful that you take into account that we're dealing with a relatively high density medium here. Now, in a very schematic form, the end result, to some extent, of some of the considerations I'll be going into in more detail, is that we have kind of a layered atmosphere, and I'm giving you the main types of regions here as a function of vertical column density, and I'm measuring vertical altitude by the vertical column density integrated from above down towards the midplane. So what happens is that there's a relatively warm to hot gas, and at a certain point there's a thermochemical transition, instability is occurred where you go from one phase to another, and what you enter into is a region where molecules are being formed fairly strongly, but they're also being destroyed, especially by far UV radiation and by ion molecule or ion radical reactions. After you go through this transition, this photodissociation region, which is pretty warm, in the range roughly 500 to 1000 Kelvin, you get to a region where essentially all the atoms have been converted into molecules. And that region is still relatively warm and can give rise to observable lines or contribute to the observable lines. And then eventually you get into a region which is pretty cool and where you have to begin to be concerned with the freeze out of the gaseous species which are dominant in the inner region onto dust grains. On the other hand, the dust in the inner regions of these disks is relatively warm, So to first order, one can ignore freeze out unless you start going out in radius. So this picture is good, to the extent it is good, is meant to apply, is what I should have said, to the few AU region. So it's somewhat similar to the familiar PDRs, but it's quite different in that there are other phenomena that occur which are more having to do with the thermodynamics of the warm gas. And this is the same diagram where, again, we have our layered atmosphere, a hot and warm partially and then fully associated molecular region. And there are different processes that are of interest in these layers. So in the top, the FUV is very important, but in this hot region, it's X-ray ionization and heating, which is the most unusual aspect of this type of corona. Then we have here things which are more familiar, the transfer of FUV radiation and its attenuation by dust and by molecular and atomic absorbers. And then you get to this fully molecular region where you still have warm, observable molecules, and here ion molecules or ion radicals. Well, radicals are molecules, so that's okay. Ion molecule reactions are important. And then at large radii, you can have freeze out. And as I'll show you in a minute, this is the region where you have your very large temperature changes. So here's a kind of recent model that we have made that involves this idea of stellar radiation of all kinds of photon energies hitting the atmosphere in the inner disk. And I put some assumptions here that are important, how much X-ray radiation is involved, how much FUV is involved, and what kind of grain surface area disk presents to the incoming radiation. And we are using generally, have been using for a long time, the idea that, which has some basis in observations that, as well as in theory, that the grains grow, the bigger guys will settle down, and the atmosphere will have a reduced amount of small grains. We know they're small grains. We see their effect in the silicate feature. And we're assuming here a moderate reduction in the grain effectiveness or effective area of a factor of 20 or so. And we've looked, of course, at different values. Now, over here are the results, and these results are always given now in terms of vertical column density. So this is the z-axis, and the top of the atmosphere is here, and the midplane is over here somewhere. And here is the dust temperature, which comes from our use of what I call the D'Alessio 1999 model, and we have I've plotted here just a few examples of molecular abundances. So above, and then I shouldn't skip around so much. Go back to the temperature plot down here, and we have here a high temperature region at relatively low density and small columns. And then there's a fairly rapid drop down to temperatures which eventually will approach the temperature of the dust in the disk. And so this is what I call the thermochemical transition, because it involves the variation of cooling functions with the abundances and the chemistry. And I want to skip over too many technical details. I'll just say that's what it is. And what we see in the hot region, of course, is that there are very low abundances of molecular hydrogen. They're not completely negligible. And as far as water is concerned, water is way, way down. And the only molecule other than H2 is OH. And then they all will rise up as a result of especially UV photodissociation being shielded, and especially in this region here before we get essentially to more or less constant abundances. But as you go deeper and deeper, you get less and less OH. You get a large amount of water in terms of abundances and of CO. And of course, the hydrogen becomes fully molecular. So this is what I would say is a reasonably successful model with lots of defects, which I'll come to, which is the main purpose for my talk, is that. And but before I go on, I want to just emphasize what the basic root of this kind of model, in addition to the radiation effects, is the chemistry. And what I have here is a diagram. OH is the keystone of warm radical reactions. Now, what is really the first step and the absolutely necessary step to a 99% certainty is that you must have H2 before you can make any other molecules. And with H2, you can, with warm gas, you can have a reasonably successful conversion of oxygen, first to OH, and then to water. And the numbers, which you may not be able to see, give you the temperature barriers that have to be overcome by the kinetic energy of the gas. Now, this diagram also applies with some revision to what Ron Allen was telling us yesterday, in the sense that the first three, the top line is the same, but the way it's done is different. In the interstellar medium, you have to have H2 to start. Then you have ion-molecule reactions, which make OH. And if there's enough H2, you may make CO as well. So this kind of idea of H2 being the first step, and then OH in some sense being the central player from which many other species are derived, applies both at low temperatures with ion-molecule reactions and here to warm temperatures in protoplanetary disks and other regions like shocks, for example. This model does not actually fully satisfy hydrostatic equilibrium. And that's just because technically at this stage it's been easier for us to basically take Fowell's models, add the gas and its chemistry and physics, and build a kind of composite model with many defects. Actually, one of them is the one you mentioned. The other has to do with the nature of the dust, which is an open question in my mind, or there are open issues there that need to be sorted out, which I come to if I don't linger too long. So in this model, I give here some of the processes, just to list them, and in particular, we're discussing here what might be called the thermodynamics of the atmosphere. And so there are a large variety of both cooling and heating mechanisms. Now, this list, of course, is incomplete. I just stopped after a while, but these are the most important ones. And as I say below, the cooling is the easy part, except for cooling that relates to dust, because then your ignorance about the dust enters and makes it uncertain. And that's important here because we'll find that the gas interaction is kind of a fundamental part of the thermodynamics. And over here, heating, that's always more difficult because you can't measure directly. But what we have been doing is looking at a sequence of processes, and these are the ones that are in our model at the present time. We were very hopeful when we began that X-rays might be the most important heating mechanism in these disks, because these stars do have a fair level of X-ray emission. But X-ray heating is deficient, and therefore a very important part of our model is heating by the accretion process. That's by the dissipation in the accretion. And I want to talk more about that. H2, here it goes. In the formation of H2, there is an important possibility of heating. And then, better known, or from the interstellar medium, is the heating when you release particles from either the gas phase or from the dust phase. So we're talking about photodissociation heating, especially from water, and we're talking about the photoelectric effect from grains. However, the grains are not that important because we're assuming that the grain area is significantly reduced, which reduces the amount of FUV heating. The main message is that I think heating is a very serious problem. I've never really been happy with our understanding of it, and shocks, perhaps from accretion, may play some role, but I'm not sure how important they are in the inner disk, and I have not actually gotten yet to the point of putting that into these modeling efforts. Every time one comes up with a heating process, it raises questions that either destroy the idea or lead me to say, I don't know. And I'll be saying that many times, perhaps. So in any case, the heating is problematical. So that's the punchline you guys have helped me with, which is how to heat protoplanetary disk atmosphere. And as I already said, we became concerned about this issue when we found there was warm CO in the inner disks of these, in the inner regions of these disks, and the X-rays failed. And so I wrote a paper with Joan Najita and Javier Ejea called Heating Protoplanetary Disk Atmospheres. And basically what we said there was, well, we should put in some mechanical heating. So what we did, following some work that I was involved in with Frank and Siani Shang and others, where we treated dissipation by mechanical agencies in a dimensional way. So the volumetric heating rate is given according to dimensional analysis with a coefficient called alpha. This formula, of course, is in the original theory of a thin disk, but we say, oh, it's generally valid, and you get, and rho is now the three-dimensional structure of the disk, and alpha is a parameter that can vary with position. And so rather than using the average alpha that people say is appropriate for two-towered disks of whatever, 0.01 or larger, we say alpha can be almost anything but over order unity. And in fact, order unity works very well and gets us the models I've described. And then along came the people who studied the MRI in the so-called shearing box simulations. And Neil Turner, in fact, came up with that sort of situation. This is a diagram of this paper, and this is a shearing box simulation with goes up and down 4 scale heights in vertical dimension. And basically, he has a heating rate which is very small near the midplane, but it's several scale heights. It goes up essentially to some fairly large value. So there was some support from the MRI theorists for this idea of taking alpha to be a fairly large number. Now, since then, I'm not sure I believe that calculations of the occurrence of the MRI in these shearing box simulations with periodic boundary conditions and other conditions and assumptions, especially Neal's use of just pure ohmic dissipation, are really all that informative. So in any case, that's in some way why I'm a little concerned about whether our idea of 10 or more years ago that it's accretion heating is correct. Certainly I'm not sure, I'm very unsure about the formula that we used based on dimensional analysis. But that's what we do. Now, there are some other important heating mechanisms that I want to talk about, and the most important one is the formation of H2. Now, on grains. Now, of course, the grains are fundamental in these disks. They not only told us that these disks are there, but they provide all kinds of information. And Nuria, who's sitting right here in front of me, will be talking about that area after the coffee break. But they play an interesting role in the thermochemical models, and in particular, they affect the chemistry because they're critical for forming H2. They absorb the FUV radiation, which dissociates molecules. And then, as I already mentioned, they play an important role in cooling the gas. And then they form H2 in excited states. And unlike the interstellar medium, the densities here are so high that these high rho vibrational states can be just de-excited in collisions and therefore heat the gas. And want to go back just briefly to this formation. This formula for the formation of rate of formation of H2 on grains, which came out of the work of Hollenbach and Salpeter and is very well known. And I've evaluated it for a parameter which is the mean size of the grain distribution measured in microns, which might be a good number for protoplanetary disk grains. And what's troubling about this formula is that any of the factors which appear at the end of the formula, which refer to the dust grains, are uncertain. And none is more certain than the efficiency of this whole process for protoplanetary disks. And in fact, in our 2004 paper, we did not include grain formation of H2 and used only gas processes which exist, because the idea was that the grains would be too warm for the H atoms to stick long enough to form H2. And however, Pazzo and Thielens came along and did some calculations which suggested that instead of what's called chemi-absorption, which is absorption through long-range forces, should be enlarged to include so-called chemi-absorption, where the H atoms actually stick through more chemical forces. And so we have used their theory, and then this formation rate becomes, in some sense, a dominant process in the whole model. And it also then becomes a heating source, as I already mentioned. And I'll skip the top part where there is evidence now after 40 years that a certain fraction of the binding energy recovered from formation actually does go into excitation of the new H2 molecule. It does not go into kinetic energy, or very little goes. And finally, in terms of another important grain process is the cooling. And so here we have a formula for what's called the accommodation, thermal accommodation, and it involves a coefficient in front, which is the accommodation coefficient. And then there's a mean speed and a dust temperature, gas dust temperature difference. Again, the value of that accommodation coefficient is very poorly known. There's work from 30 years ago by Hollenbach and Chris McKee, and that work is based on laboratory experiments that the numbers that come out of the work to get this accommodation coefficient are based out of laboratory experiments of atoms on tungsten. And I don't know whether those results for tungsten are really relevant to interstellar grains, and very little has actually been done on the subject in the intervening years. So let me speed up and just show you the thermal model that I'm so concerned with. And again, we're plotting as a function of altitude the different heating and cooling mechanisms. And a couple, the two on top here, the red one is the accretion heating, which plays a very important role all the way through the disk, atmosphere. And the black one at the top is this dust gas cooling formula, which I just mentioned, that I'm not all that certain about, but have made a best guess as to what it is. So in any case, what happens is that in different regions, there are different of these processes are important, but it turns out that these macroscopic formula that I've discussed, such as accretion heating and dust gas cooling, they play a role all the time. And the last part of my talk has to do with water. There's now extensive evidence that, except for some special reasons about the disk itself or the source itself, water is easy to detect in T-Tauri star disks. And the Spitzer results show a whole bunch of those spectra. And the table here shows the results of a modeling of the observations by Carr and Najita of several disks. And you can see, and that model, I should mention, is very difficult and has not been done in a completely satisfactory way, in that a usual model is a slab, an isothermal slab, to replace the disk atmosphere. And the net result is that, accepting this modeling technique, is that there is a fair amount of water. Column densities in the middle are of the order of 10 to the 18th per square centimeter. Characteristic temperatures of the model are 600 Kelvin, and the water occurs in the inner 1 or 2 AU. On the other hand, there are a lot of disks where water isn't detected, and I don't think people have spent a lot of time yet on understanding why. This is a repeat which just discusses what affects the water in terms of its destruction, which is photodissociation in the transition region, ion molecule reactions here, and destruction by atomic hydrogen, reversing the formation. So I'm now at the conclusion part, and sorry I didn't get enough time to talk more about the details of the water situation, but the best positive conclusion I can make or assert is that the models show that you can make a substantial amount of water, like 10 to the 45 water molecules, which is I don't know, maybe that's the Mediterranean Sea or something, you can make a fair amount of water in situ, meaning locally by local chemical processes dependent upon the temperature and the ionization and FUV. It fails to explain the amount of OH. And we've had that problem for a couple of years, and I don't have any solution to that. I indicated, but want to emphasize again, how closely water and molecular hydrogen are connected. And the two of them grow together in the transition region. And then the key role played by dust in its many different forms, okay? And one thing that's kind of interesting is that if we lower the amount of dust in the atmosphere, decrease the surface area by 1,000, let's say, which is what I think Ferlin et al. Recommended for AA tau, then the water goes away. So there's a connection between the dust's physical properties, largely determined by the silicate feature, and the abundance of water, and we're starting to look at that in a little bit more detail. But I wanted to mention it to some of you here. That's a result that we're just getting ready, we're starting to write up. And then, as I already indicated, I'm concerned about a lot of the underlying physics that's involved. So what I tried to say here is that a lot of things go into understanding the inner disk. I think multi-wavelength observations are important. Even with ALMA, we will just begin to reach the outer part of the region that I'm most concerned with, and which is the region of planet formation and jet production and so on. The external radiation is key, and the thermodynamics and the chemistry work together. And again, H2 and water are very closely connected. Now, I have here some ideas that I'm not, that either say, theorists interested in MRI, I'd like you to really come up with a better description of accretion through the disk, and especially of the heating, so we can put them into the models in a more reliable way, or other ideas are of interest, that some of which we'll be looking at. So most of this work that I've talked about today is done with Mate Adamkovic, who is a senior scientist, research scientist at Berkeley, and Joan Nadicha, many of whom know. The spirit I had when I was preparing this talk was that I wanted in some way to express my appreciation to Nuria and Paula for their models. I told Paula yesterday, she gave me in 2001, a long time ago, 2 models. And I'm still working on the first one and haven't gotten to the second. And then, of course, it's an appreciation of long-term collaboration and friendship with Susanna and Frank, who have helped me so very much in my work. So, Luis and Susanna, congratulations, and all of CRA.
Al, so there have been 2D hydrodynamic calculations of X-ray heating in order to try and photoevaporate the disk. Have you looked at those calculations in any way to compare to one of your models to see if, because they're getting very high photoevaporation rates, and I'm just wondering whether they're, there's something that they're missing in their...
No, I did talk to people who were involved in photoevaporation, but mainly the, Kathy Clark's group. And I told them from the very start that you should use X-rays and not just FUV, because the X-rays reach a deeper region and you can get a larger mass loss rate. And then that did come out of that work, but then there's the question of evaluating its astrophysical significance, and I haven't gotten into that. I don't think much of what I said today is invalidated in the sense that, yes, the upper atmosphere I've been talking about is not a stable atmosphere. It is we're losing mass there, sponsored by, among other things, photoevaporation. But I think the physical properties of that low speed are not going to be all that different than what I told you today.
In regards of these models of polar normal data, I always wanted to ask you, one of the things, I'm sorry, they are talking about the Colano models for photoevaporation. One of the things that they say, they criticize the Lyman alpha cooling, but then they actually use things like they use a CAN, program, and they have magnesium 2, calcium 2, and the standard things that you find in stellar atmospheres. But of course, when we've been looking a little bit about heating and cooling and putting the gas temperature with Paola and I. And then one of the things that Bergin has told us is that in general, it is assumed that all the metals are in the dust. So that magnesium, calcium 2, they are not real coolants.
I never believed that.
It's not true?
Well, the point is this, that in modeling the interstellar clouds and in this, people just say the gaseous abundance of heavy atoms is very, very small, right?
Yes.
They start that way. But there's no proof of that. We don't even have any proof of that for molecular clouds. We know there's dust, but maybe only 50% or 70% or 90% and now we're talking about not the volatiles, right, but the ones that stick and form the grains, not sulfur, for example, which is likely in the gas.
You're talking about magnesium,
Yeah.
things like magnesium and calcium.
Yeah. And if you saw the paper, our most recent paper on X-ray irradiation, we have a model where we just use the interstellar depleted abundances, which is probably much too high. So we could talk about that, but
yeah.
I have never believed in just putting everything, all the heavy elements into the grains, and we don't really know what that is, and the way to find out is something I've been very interested in, and if you are, please go ahead. We did do a fair amount of work in the beginning on the various lines of these heavy elements, and that's the only way to do it. Is you have to go out and measure them in disks.
Yeah, because if calcium 2 and magnesium 2 are important coolants in the disk, the mission should be extended. So
that's right. If
should go and
right.
have an HST proposal on that.
Yeah.
Okay.
Yeah.
Al, you commented on the comparison between interstellar chemistry and disk chemistry, both similarities and differences. But another class of objects that perhaps it might be good to bring experts in, planetary atmospheres, where the upper atmosphere to lower atmospheres has similar range of densities and temperatures. Yeah. I also wonder whether, things like cloud formation may not occur in disks.
I say yes to everything you said. What I was hoping when Mate Adamkovic started to work with me is that we would go in that direction, because he actually is a planetary scientist who works on the atmosphere of Titan. The connection, but to go back to the chemistry part, so one could learn if one only had the time from these other fields. The chemistry that is used in our models is not interstellar chemistry, although it has much in common. We have, at the moment, about, 1,500 reactions. They include the important interstellar ones, but they also include the chemistry of the Earth's atmosphere. That is in some sense, it's a primary source of information about the warm chemistry in protoplanetary disks. And we have gone through every single reaction in our model, looking at the chemical literature, and then, of course, a fair number of reactions, we can't find the information, and we have to do what everybody else does, which is make intelligent guesses, or make guesses. So, yeah, connecting this with comets, with planetary atmospheres is very important. Now, the densities here are higher than interstellar, but they're lower than in some of these other applications.